recording, Anna.
Okay, so thank you very much, Professor Lahcen Maniar, to accept the talk, to give a talk in our seminar. We are happy about that. So let me just say some words in order to present you. So Lahcen Maniar is a full professor at Qadi Ayad University in Marrakesh. He coordinates the team of control of system and interaction in Marrakesh. He supervised nearly 25 PhD theses with many of his former students now serving as a professor at various universities across Morocco. Professor Maniar is the author of over 100 papers on control and inverse problems. He has been honored by Alexander von Humboldt Fellow, and currently he's the president of HBNet, a Moroccan network focused on control theory and interaction. Today he will speak about heat equation with dynamic boundary conditions, WELL-POSEDNESS, and null controllability. So thank you very much, and you can start.
Okay, thank you, Anna, for this invitation. Thank you for all organizers of this prestigious seminar who was invited before the most, I can say, famous people in control theory and EDP also. My talk about heat equation with dynamic boundary condition, as you see in the title, WELL-POSEDNESS and null controllability. Here, I will talk about heat equation, which is a famous equation, much studied from semi-group point of view, from stability, from control, also questions, inverse problems, and many, many other questions. Here, I start with this is the famous equation, which just, the simplest heat equation is just yt equal Laplacian of y on some domain omega with the boundary gamma. And in general, the most studied equation is studied with directly boundary condition, Neumann boundary condition, and also with Robin boundary condition. Here in this talk, we are interested in another kind of boundary conditions. Let's say Wenzel boundary condition is called the first condition where we find a second order operator at the boundary. There is also dynamic boundary condition. There is Favini, Goldstein, and many others. When you find another, can say evolution equation at the boundary, and this the word dynamic comes from this derivative here, and with this term Neumann of the first variable. Here is the trace y trace gamma is the trace of this y epsilon. And there is also this general dynamic or this general Wenzel boundary condition, which is given by a Laplace Beltrami. Here we add the Laplace Beltrami at the boundary for the dimension n bigger than 2. Otherwise, if n equal 1, this term is vanishes. And we have we get on this dynamic boundary condition. Okay, now we consider this heat equation with all them general boundary dynamic boundary condition, which, as I said, is a heat equation in the bulk at the interior of a domain omega, and another parabolic equation or another heat equation, if you can say, on the boundary gamma. And this connection of y gamma is just the trace of the internal variable. This models comes from fluid dynamics, precipitation of rainfall, infiltration into soil, heat transfer, flow of heat for a solid in contact with the fluid. Population dynamics, also diffusion of bacteria from a solid to its surface. And this model is derived physically from, physical laws by Goldstein in this beautiful paper in 2006. And recently in 2020, there is another derivation, another model, another equation modeled by Zauer, where here we find here in this connection between these two variables is not only the trace, but there is also a Neumann term here. It's a general, I can say, dynamic boundary conditions. Okay, this equation, we start from the well-posedness point of view. It's a common methodology to write this equation as a Cauchy problem in a L2 space, or in a product L2 space is L2 in omega times L2 on gamma. And the operator E is just this operator here, with the domain is just H2, where H2 is just H2 times H2 with this trace condition should be added here. And we have shown that this operator E is self-adjoint and generates an analytic C0 semigroup on L2. And this will gives us a maximal regularity of the solution, the existence of mild solutions, that is this well-posedness estimate here. And also if y 0 is in each one, then the mild solution is a strong one and is given by this variation of constant formula here. This is for, I can say it has some references. There is a lot of Gall, Favini, Goldstein, Gracilli, Miranville, and many others who studied this equation with dynamic boundary condition from the stability for variety absorbent or many other questions. And here, as I said, we have considered the easiest or the standard heat equation. Here we take only minus d and delta here just constants, but we can take a general or elliptic operator, second order elliptic operator with coefficient depend on x, or also in time. Also we can also here a could be also depend on x and in time, and then we will get instead of semi-groups, we will get evolution families, and we still get the maximal regularity of the solution. This is just to make the talk clear. And okay, for we can also take from the control questions, we add here an internal control on some small region omega, or we can take also an boundary control on some gamma 0 on parts of gamma. And we want to study the controllability or the null controllability in the sense of this definition. We say that our system, 4, not 1 is 4, is null controllable or boundary null controllable at fixed time t, if for all given y0 in L2, and boundary also initial states, and in L2 gamma, we can find an internal control V or a boundary control V such that we have these two variables here are equal 0 at time t. This is the new thing here is, the new definition in this for this kind of heat equation. Okay, here we can say I can remark that this two initial states here are not don't need to be connected. I mean, we don't need to have this one as a trace of this y0 here as here. I mean, just two functions, separate functions in L2 omega and L2 gamma. This is a point also here. Okay, from for this null controllability question, I mean, it has studied from many people from yes, I start by static. In this static boundary conditions, we call static, which is directly Neumann or Robin, by Lubo Robiano and Forsikov-Manovilov, as you know, using Karloman estimate. And also there is after there is a lot of works in this equation. We can say this. Cite Albano, Canarsadi, Teresa, Zuazwa, Yamamoto, and Guerrero, and many other. Fernandez, Cara, Puyel, Bin Abdallah, and many. And sorry if I forgot someone. Yes, this. I mean, the seminar is now international seminar. As in, I cannot cite everyone from in. Sorry if I forgot someone. For the dynamic boundary condition, when we start to work on this question on 2013, we didn't find much references or much works done in case of dynamic boundary condition. There is a paper from Vrabi studying the approximate controllability, but when is controlling all the region omega. And also we find another paper, optimal control, for considering the optimal control. And also there is a paper in Nickel and Kampf from Tübingen University. They studied also approximate controllability in this kind of dynamic boundary condition, but for one dimension. After, many years after, we discovered this paper of Cornelio and Guerrero, who studied controllability and observability of an artificial advection diffusion problem in one dimension. I don't remember at which year we discovered this reference, in 2017 or 2018. We didn't cite it in our first paper. We didn't know. I knew also that Philippe Chaffez da Silva did in his PhD thesis with Zwazwa. I met him in Binaski, in one seminar of Binaski, and he told me that he has some results about stabilization of wave equation with this kind of dynamic boundary conditions. And I invited him to Marrakesh. He spent 1 week to work together, but unfortunately or fortunately for him, he got a position in Brazil, and yes, and now we are far away from each other. Okay, I start with the internal null controllability, where I consider only an internal control V in this small region omega. And this is, as you know, the solution, as we have seen, we can be written like this by this variation of constant formula or Duhamel formula like this, where this operator is just the same group, given by this integral. And we know, as for the heat equations, the null controllability is equivalent to this, the image or the range of this semi-group operator is included in the range of T, of this operator T. And by the Douglas lemma, this is a famous lemma in control theory, now used so much, is equivalent to this inequality here. Because in general, as you know, to show the surjectivity or the embedding of images is difficult. too difficult even, and we prove it by this inequality here. And as we can, if we compute this joint here is also, there is a joint here, but the semi-group is self-adjoint operator, and then we keep the same E. And this now this writing this the solution of this adjoint system by this equation, we can write this operator estimate, we can say, as this observability inequality. The people working on control theory, you know, all this trick. I mean, this methodology is the standard methodology to prove null controllability, is to prove an observability inequality. The difference between heat equation with static and dynamic boundary condition is this term here. In our case, we should control all the energy of the system, the joint system at time t0, and also the boundary variable also by the same, I mean, by this term, which is only on omega, which is an internal phi. We don't need to get also a term on the boundary here at the right. This is the idea or the difficult task here in this. And as I said, as you know, to prove internal Karloman estimate, to prove inequality observability, we should prove some Karloman estimates for this equation, which, as I said, it's proved by Forsikov, Vilov, and Lobo-Rubiano when we have here static boundary conditions. Now we want to prove the Karloman estimate, or Forsikov Karloman estimate, not Lobo-Rubiano estimate. Sorry, in this case of dynamic boundary condition. As you can imagine, if you have done at least once the computations for Karloman estimate for wave equation, even for directly boundary condition, when all the boundary terms are absorbed, we can you know what is, I mean, how difficult, how huge computations are. Then we can imagine when we add another equation here, when another parabolic equation and the boundary, we can say the difficulty is doubled by 2, and we suffer to prove a Karloman estimate. For the Karloman estimate, we need a weight functions, which is the same. Fortunately, we took the same eta for the heat equation with static boundary condition, is this famous eta function, which satisfy this estimate, which will plays a key role in the estimates. The alpha and zeta functions are the same as in the heat equation also. And what we proved is with this Karloman estimates here, we control the internal variable phi and internal and boundary variable phi gamma on gamma and its gradient also. This is tangential gradient here, and also the Neumann term, which is here is the coupling term. If you remember in the equation, this is this term, I mean, we can say the bad term in the computation. And this is proved. It is estimate only, as I said, only by this internal variable phi on the small region omega, plus this inhomogeneous terms, which we will take null after to obtain observability inequality, but they serve to prove other other things. If we want to study inverse problem, for example, source inverse problem, or for the semilinear also, the semilinear, if you have a semilinearity on internal and also at the boundary equation, these terms play roles. Okay, now if we have this Carl-Lehmann estimate, as I said, to show this Carl-Lehmann estimate, we follow the strategy of Korsakoff, and yes, we define the symmetric, anti-symmetric terms for the internal equation, and also symmetric and anti-symmetric terms for the boundary equations, and we try to absorb the boundary terms because here we got a lot of boundary terms which does not disappear. I mean, because we have this equation at the boundary. We don't have even Neumann or Dirichlet boundary condition that we had. I mean, many boundary terms which should be absorbed here in this equation, in this estimate. Okay, now with this Carl-Lehmann estimate, we can prove our inequality observability. This just using, as you know, using just this term and also this term. I mean, we don't need this first first terms for the inequality observability. Okay, the observability of the adjoint system, of course. Now now by equivalence, or by this Douglas-Lehmann equivalence, we got the null controllability of our heat equation with dynamic boundary condition, and this is a result done with Meiris and Schnaubelt from Wuppertal University in Germany. Many years ago, 8 years ago now. Okay, after we consider this equation, heat equation, usually with this dynamic boundary condition, but here we consider this gradient term or this drift term on the equation. But C is, we consider C and D just L infinity functions. And you know, as in the heat equation, this problem is considered for the heat equation by these authors already. To show first the well-posedness of this equation, we use perturbation theory, semi-group theory on perturbation of semi-groups, and we write our equation as the sum of A0 plus B, which is B is B1 and B2, which is just this potential EB and this gradient terms, which are, in the case of equation without drift terms, we had only this potential, which has a bounded perturbation of E0. But you know, this is unbounded perturbation, and one should that it's as a good unbounded perturbation, which we call E0 bounded operator with null E0 bound. This is important to get this result. The sum of E0 plus B generate an analytic semi-group. And also we have an idea about the interpolation between L2 and H2, which is just H1, as in the absence of B1. I mean, as in the case of heat equation without drift term. The equation 9 is well posed and has maximal regularity. I mean, we still have the same regularity for the solution of this equation. For the controllability task, we should consider, as you know, the adjoint system. But for the adjoint system, we have these terms, this divergence of psi C, and all these red terms. You now assuming C is just L infinity, this function is not differentiable, is not derivable. Then this divergence term is here is in a weak sense. That means this term is in some extrapolation space. We can say if psi is in L2 omega, then divergence of psi is in I cannot say in H-1 because we have here only Laplacian without any boundary condition, that we have no C0 semigroup on L2 omega. This is the point. What we did is to consider this this coupled the equation, and to take this this term as an addition or additive term of this equation of this our E semigroup. And we show that this is this we can say, if we can write E plus B or E0 plus B as here. A0 is the same as in our case. Then, but here in this adjoint system, B is not in L2, and it goes in some extrapolation space. The extrapolation space, according to E0, is some kind of H-1 space, if you can say. If here we have this H1, this will be some H-1. And we should define all the theory of extrapolation for this kind of product spaces. And we could prove the existence of mild solution, strong solution, and this is a result obtained with my student Khotaibi and Dilio Menolo from Hagen University in Germany, and Abdelaziz Ghandi from Salerno University. This is I mean, recently published in this Nachrichten journal. Okay, this is from for the well-posedness of the adjoint system. Now for the controllability result, we should, as for the heat equation with static boundary conditions, show a new Carl-Newman estimate with these red terms, with these bad red terms, if we can say. Okay, then writing this terms as F0 F and F0 gamma, we got now we get a dynamic boundary, a heat equation with dynamic boundary condition, but with, as I said, with some H-1 terms. Divergence of F, and F is not regular, and also at the surface, and exactly the same. Now, as done by Forsikov, Manovelov, Guerrero, and Fernandez Cara also, we tried to prove a Carl-Newman estimate which estimate these terms by here I put this these terms in blue to see that here we need to get F and F gamma, and not divergence of F as in this. Here I can mention that we cannot use our previous Carl-Newman estimate because this F0 plus divergence of F is not in L2. Then it's not as in the previous term, this small f, which is an L2 function. But we need to get a Carl-Newman estimate with the f term, which is an L2 function. This is important also. With not the divergence, not an H-1 Carl-Newman estimate, but we need an L2 Carl-Newman estimate. And now with this Carl-Newman estimate, if we take, for example, if I consider this, in my case, this F0, F, just these terms here, then I can get this Carl-Newman estimate. This F, these terms can be, can be absorbed by, and we got our what we need, what we are looking for is a Carl-Newman estimate. This Carl-Newman estimate. Okay, now with this Carluman estimate, we can prove this observability inequality by the same trick, the same technique, and this is a paper result published in this paper Kotabi and Maniar. Okay, in 2020. Now let us move to the boundary control. We consider here a control on a part of the boundary in some gamma 0, and we want to prove the null controllability by, as we did for internal control. But you can as you know, that for the heat equation with static boundary conditions, we can study the boundary controllability by the internal controllability by enlarging this technique, this trick of enlarging the domain omega. This we did it in our first paper with Roland and Martin, and we got this result. But it's not a sharp result. I mean, we need initial state to be H2 and also to satisfy this, to be in this space for some P. And we got a controllability result by the same trick as for Chekhov-Manovlov, as you know, for the heat equation. But it's not a sharp, I can say, result. And without, if we could obtain controllability results by using Carluman estimates, and which we did here, and now to obtain the controllability by observability, and our observability estimate is like this: is phi gamma here on gamma 0. Now is the boundary variable here on gamma 0. This is we call boundary observability inequality. And to prove this inequality observability, we should prove a new Carluman estimate. Now we need an eta function, this famous eta function, which is not the same as before, because I mean we need that the gradient of eta should be non-zero on all omega bar, and this is also as a restriction. And as we have also this third property, this Neumann term of eta is negative, strict negative only in gamma minus a small region gamma on the boundary of included in gamma 0. Not as before. If we remember, we had this estimate on all gamma, and this is play the rule, and this will, as we will see, the alpha and zeta function are the same. And what we got is we could prove this Carluman estimate for the boundary control, and we can say there is a difference in these potentials. They are not the same. Is 3 lambda 3, and this are not the same as in the case of internal controllability or internal Carluman estimate. And to obtain this estimate, we did the same computation as before, and try to absorb all the bad terms to the left, but all terms go. 112. Only but not this term 16 term here. This is the normal derivative of eta on gamma 0. This is gamma. This term is not negative as before. This is the term to remain at the boundary, and it should be absorbed by another trick. As I said, this term 16 term is appears also in the internal control, but with this estimate on all gamma, this is just this is less than this minus constant c, and this could could be, I mean, absorbed to the left, to the right, to the left side. But here we have this term, this I mean has no sign. It's not. We don't know if it's not negative or positive. This is, and to absorb this term, we need more regularity on the solution of this inhomogeneous adjoint equation with null final term or final condition. Yes, we proved this estimate that the solution phi belong to H2 and H1 in L2. If F is in L2, we had the maximal regularity, and we have this estimate, which we try to prove that I mean explicitly, we give explicitly this dependence on time t is important, because as you know, we want to get observability constant depending on time capital T. This, I mean, the dependence is important for further questions. And also, if we have F is in H2, we had our function is in H4. I mean, it gain more regularity, and we got this estimate, and this estimate will play a role to absorb this bad term and to obtain this observability inequality here. As you say, also these exponents are not the same as in the internal term. Okay, now we get the observability inequality. That means we are done. We got this the boundary controllability for any initial state in L2. This is what we gain here. Not as before, we have no restriction on the initial states using this trick of enlarging the domain omega as done for the heat equation with the static boundary condition. This is a result also published with my students Shorfi, Gmai, and Khotaibi. Okay, now I am at the end of my talk. As if you have, I mean, noticed the remark that all results we done in this works are done for this Beltrami term delta is positive, should be positive. I mean, this is important to get this Karleman estimates, or otherwise we don't know what happens. Or if delta equals 0 and the dimension is equal 1, because as I said before, in one dimension we have no Laplace Beltrami term. That means delta equals 0. But for one dimension, we have the tangential subspace is just the 0 is just 0, and all these bad terms are I mean vanish automatically. That means we got the same Karleman estimates as here for free. I mean in one dimension. But the case where delta equals 0 and the dimension is bigger than 2 is still open until now. I mean, I give this talk several times, and I end with the same I mean open problem. We didn't know how to solve it. I mean, if someone is interested and or has an idea, I will be thankful. Okay, I have here some reference. I mean, as I said before, when we started this working on this heat equation with dynamic boundary condition, we didn't find, or there was no, I mean, not much works. After our first paper, there have many papers appeared. And I can say the first one is 2017 by Cyprien Gall and Louis Thibault, and I mean is by the way he's the first speaker. I mean it's not Isa Hazar, I can say. There is also papers published recently by Mercado, Roberto Morales, and Zamorano, and Carino, and Morales also. And also from, as I said, our first paper, there is a lot, we did a lot of works in our team also in inverse problems of heat equation with dynamic boundary condition. We studied optimal control with two controls, with Nash, Stackelberg, equilibriums also. 6 or 7 PhD theses were, defended in our team on this topic. It's now 13 years ago. This is okay. Thank you very much for your attention.
Okay, thank you very much, Professor, for this wonderful talk. So let's ask the audience if there are some questions, comments. Yes, you can use the microphone and also write in the chat. So please go ahead.
I have a question.
Yeah.
Yeah, I would like to know what precludes you from using delta equals 0 in dimension n greater than or equal to 2?
Can you repeat your question, please,
Yeah.
Luis?
Why is taking delta equals 0 difficult in the case of dimension n greater than or equal to 2?
Yes.
For the heat equation, but because for the we know that we can do it.
There is problems also in the wave equation, you can say, because
for the wave equation, we know we can take delta equals 0. That we know.
No, Thibault. We can discuss if we want.
Yes, because we prove in our work we can take delta equals 0 for the wave equation, just for the wave equation, not the heat.
Sorry,
you can look at the heat, but for the wave equation, we can take delta equals 0.
Thibault, our Carluman estimate or our observability inequality is this one. Is we want to let only phi on the small omega, not the gradient as you have done in your work. With the gradient and tangential gradient and many other terms at the right.
In our case, we are working on the boundary, but for the wave equation, you need for the wave equation. Because for the wave equation, you don't have regularity,
Yes.
But you know that. So for the wave, you don't have regularity. So first, your control region must be large enough, right?
For the heat equation, as I said.
For the wave equation, I'm talking for the wave.
I am working.
For the heat equation, you do have regularity.
I am working on parabolic equation. Let me answer on the parabolic equation.
You have regularity. On my point is, what is the main obstacle to taking delta equals 0?
To absorb the gradient, tangential gradient term from the right. You need to use the Neumann term. But the normal term is here. Is in this equation, is given as not as in the static equation, is given by this equation. And here you see that there is a second term here, and then you need this term delta is important to get the regularity, to H2 regularity. Otherwise, we don't get more.
Okay, I see.
We lose regularity.
Okay, all right. Thank you.
Yes.
Thank you. Other questions, comments? I have one question. What about the semilinear heat equation? So
Yeah, yes, we did also semilinear. I didn't want to talk about it here. Yes, I mean, when you get Carloman estimate for the inhomogeneous term, if you have, then you can get semilinear also in this space with weight function with this Carloman with this weight functions from Carloman. Yes, we can do also semilinear even with the blew up terms. I mean, not only Lipschitz terms, as done by Zwazwa in this heat equation. You can take S alpha log beta, something like that. You can, I mean, you can go even S.
okay. So thank you very much. Are there other questions
Chat.
in chat? No, I don't see any. So if there are no questions, so let's thank the speaker again. Thank you very much for your wonderful talk. And
there is a question. Sorry, there is a question here on the chat about
yes, sorry, yes, Luis Diapu.
Yes, Luis Yapu. Yeah, maybe. Yeah. Well-posedness with semi-group theory for time-dependent coefficient in the diffusion. In the diffusion is well known. He is asking if there is well known. No, I mean, if the coefficients are depending on time, if not, I mean, if only the potentials are dependent on time, you get some, I mean, is a non-autonomous perturbation of an autonomous operator. You get E plus BT. This is easy to study, I mean. But if your diffusion terms B, D, and delta depend on time, then you get what we call evolution families, and they are parabolic, and then we can do the same. I mean, you get ET plus PT, then yes, just because I mean ET, it's, I mean, yes, use it's depend. I mean, it generates an evolution family which a semi-group with two parameters T and S. Yes. Okay.
Okay. Are there other questions? Okay. If not, we thank you again.
Okay. Thank you, Anna. Thank you for the invitation. I am honored to participate to this seminar.
So let